So here we are with graphing motion. And before we start, I want to start by talking about what motion actually is. All right. Motion is a change in position. So motion can be a change in position. So you're thinking about a distance, you have a starting point, you have an ending point, you have movement in general. You're changing from your original position or changing from your starting position. Okay, so that is what motion is. Now, we want to graph motion. So if we're graphing motion, we tend to think about our just our regular graph. We're just going to deal in this one quadrant, and so we will deal with that. Now, what goes on which axis? Well, this is a distance versus time graph. And why is it a distance versus time graph? It's distance versus time because since we're having a change in position, we want to A, know what that change in position is, and so we need to know our distance, and B, we want to know how quickly or what was the time frame between that change in position. All right, so our time, which remember with time it can typically go with like, hey, we might be finding a rate, and you would be right. I'm jumping a little bit ahead of myself, but we will get there. And so when you identify, you have the title of your graph. You always need a title. And you also need to title your axes. All right. So this is distance. If you go back a little bit, you'll say it's like, hey, I remember that the y-axis is our dependent variable. And you're right. Here too, distance is the dependent variable based on what's changing, which is the time. Okay, so we have our distance and our time now. And now I want to just graph a basic graph for you. Very simple, just a straight line just like that. And you might see it as just a one-to-one slope, and that's what I intend for it to be. It's just a very simple graph. Okay, and so now that I brought up the word slope, what is the slope? How do we find our slope? Our slope is our rise over the run, okay? Or you could say the distance over the time. Does that ring any bells to what this slope could represent now? That's right, the average speed, all right? In this case, we're actually looking at the velocity, all right? So you could say that velocity average equals distance over time. And why is that? Because velocity, remember, is both the average speed and a direction. And look at the graph. We do have a direction. All right? And so, like I said, I was just intending for this to be a one-to-one graph. And so if we have a distance that's measured in meters and time, which is measured in seconds. So if we have a distance of 1 meter and a time of 1 second, all right, our velocity average is going to be 1 meter per second, all right, because we just divide those like we had before, and we continue to do so because it is the rise over the run, and that will give us our slope. But notice that we have a velocity, all right? Remember we said that velocity has both a speed and a direction. So we look at this, and this gives us our speed, but since it's just a number by itself and there's nothing in front of it, we can also say that this is a positive one, or it has a positive direction. All right, so this is our velocity or our slope. All right, because it just goes 1, 1. If we had 2 and 2, or 3 and 3, it would all be on the same slope, all on the same line. All right, so that is how we graph motion. And this is just, like I said, it's a it is just an object that's moving 1 meter per second. Okay, now let's look at another example. So we'll set up our graph again, distance versus time. And we'll make sure you have your units on your graphs, because those are important as well. All right. Now you have an object just like before, and it's going up on a 1-to-1 slope, so 1 meter per 1 second. All right. But then it kind of has a horizontal part to it. All right. And what do you think is happening on this horizontal part right here? Well, if you look over, you remember that this is talking about distance. And since your distance is on your y-axis, there's no change on this y-axis. And so this part of between this section and this section, this object is no longer moving. It is at rest. It doesn't change on the y-axis, but time continues to go by. And so this object is at rest between here and here. All right, and remember this was our plus one slope. All right, now once it took a rest, then it had a slope just like this. All right, and remember that we said that our slope was our rise over the run. All right, so is this rising? No, it's actually going down, and so we'll have a negative rise while our run is still positive, because you cannot go back in time. You can't go this way with time. You can only go forwards. You can only go to the right with time. All right, so since we have a negative rise, and this was you have your 1, and your 1's there, and so this would be 2, and then this part would be 3. Yes, I'm sorry, it's not to scale. I'm not the best artist in town. But this is the point. So we have 1 second, 2 seconds, 3 seconds. All right. We went up 1 meter. We stayed stationary for an entire second, and then turned around. All right. We'd say we turned around because we have that negative velocity, or we have that negative 1 meter because we went back to 0. We went back to our original starting point, and time still continued on. All right, and so between here and here only took 1 second, or 1 second. That gives us a slope now of negative 1 meter per second. All right, or a velocity, which is our average velocity, I don't want to confuse you on that, of negative 1 meter per second. We have a negative velocity because the slope went down. In this case, it went back to 0, back to its original starting point, and so that's where we end off.